Okay, all right, so we're back. I want to start now talking a little bit about the actual AASHTO LRFD specifications. Now, first off, if you ever see a hard copy of the AASHTO spec, here's what you're going to see. You're going to see a notebook that looks like it belongs in a cartoon because it's about this thick, okay? You think I'm joking. I have a PDF of the spec here, and if you notice, oh, what the heck? I hit the wrong button there. But if you notice, let's see, here's the spec. Look how many total pages are in the spec. 1,704 pages. So, of course, I will expect you to memorize every single word, formula, equation, term. That was a joke. Not a very funny one, apparently. We're going to cover pieces of the spec. We're actually going to maybe start to dig a little bit into the spec today so that you're a little bit familiar with how it's organized, what it constitutes, what's going on with it. It is built, obviously, around LRFD, and the very first section of the spec is based all around that. A lot of this book we won't even touch, okay? So don't see this 1,700 pages and go, oh, goodness. I mean, don't get me wrong. The first time I saw the bridge spec, I was like, I really want to do bridges. But it's really not so bad once you get used to it, and once you get used to its format. Okay, so let me go to the slideshow a little bit and talk about some things, and then I want to go to the code, and I want you to see where I'm pulling this stuff from. And you go, okay, now this is where he's getting at. Okay, so if I were to look at the grand organization of the code is broken down into 15 sections. Now, a lot of this we're going to look at. Some of it we're never going to touch. Okay? So like Section 1, Introduction, Section 2, General Design and Location Features. Section 2 has some general parameters and design-related stuff that might help us out a little bit later on. You'll actually find the live load deflection limit in Section 2. It's funny how the code says that there is an optional live load deflection limit that every single state in the U.S. Employs, so it really ain't that optional. So that's just the way the codes are sometimes. We're going to talk a little bit today about Section 3, the loads and load factors. We won't probably get too heavy into Section 4 until maybe next week, if not the week after. Section 5, concrete structures. We're only going to touch a little bit of this, the stuff that's relevant, and we might talk a little bit about pre-stressed design later, just to sort of, close the loop with stuff you've learned before. We've already used some minor provisions already, because when we did section properties, where did we get our cover requirements? 2.5 inches from the top, 1 inch from the bottom. We got that from Section 5. Okay. Section 6 is going to become our go-to document for a long time later on in the semester. That's the section on steel structures. Particularly, we're going to be focused on 610, which is the section within there on I-beams. Okay. So you'll have like 6.9 on compression members, 6.8 on tension members, and what have you, 6.6 on fatigue. We're going to be spending a lot of time in Section 6. Now, Section 7 we aren't even going to look at, aluminum structures. We really don't build that many aluminum highway bridges in the United States. Okay. Section 8, wood structures. I mean, yeah, you see some timber bridges here and there, but not worth it spending a significant amount of time talking about it in this course. Okay. Now, decks and deck systems, obviously we need to talk about that. When we actually do deck designs, though, a lot of this is sort of done for us. We use a different method called the empirical method. There's really not much design. You just look at it and go, here's how much rebar you need. I'm not kidding. It's basically that simple. If we have time, I'd like to give substructure its day and talk a little bit about foundations, walls, abutments, piers, things like that. If we have time, I mean, I want to make sure that we're focusing on the superstructures stuff enough, but if we have time, we'll cover it. We won't talk about buried structures very much. We may, if we, later on, I would like to cover some West Virginia specific topics, so we may talk a little bit about culverts and things like that. Not really much to talk about, though, in terms of railings. Joints and bearings, we will talk about, specifically elastomeric bearing design. The elastomeric bearing is the device that transmits the load from the beams to the abutment. Or elastomeric bearings are a very common device. And I mean, there's other ones out there, but for these types of bridges, elastomeric ones are arguably the simplest way to go. They allow for a significant amount of movement of the beam, which is really nice if you've got thermal expansion and contraction to consider and other things like that. Also, not too long ago, they actually added the design of sound barriers to the bridge spec. You know, go down the interstate and the big walls that protect the neighborhoods from all that sound pollution and whatnot. They actually added that not too long ago. Can't remember which edition. Okay, so let's start off with Section 1. You all have Section 1, like right in front of you. So, you know, Section 1 really outlines basic LRFD design that we are going to use in the world of bridge engineering. And if I go to the AASHTO code, you know, let's start off. Let's actually look at this. So, all right. So here's Section 1, start off, table of contents, and what have you. All right. There's an introduction. Usually each section begins with an introduction that defines what it is that this section is meant to govern. So if it was Section 6, it would say, this is meant to govern the design of steel structures and what have you. One other thing I want to point out is just the general format of the document overall. Okay? Notice how there is a Section 1.1 and then there is an accompanying C 1.1. Everybody see that? Everything on the left is the actual code that we use, the actual document. These are the guidelines that we must follow. Everything on the right is the commentary, okay? So if there's something over here on the left you don't understand, probably there's something on the right that can help explain it, okay? Or at least tell you why it's there, okay? A lot of the stuff that is added to the code or changed in the code, why they do that, it's explained over here, all right? Sound good? All right. So, you know, Section 1, we got the introduction and the scope. Typically, for each section of the code, you will see a series of definitions on terminology. So, what is a bridge? Maybe I should have answered that on day 1. Goodness, I don't think I'm doing very good if I didn't define that. So, but what does the code define as a bridge? Any structure having an opening not less than 20 feet that forms part of a highway that is located over or under a highway. That's a pretty, I think, basic definition we can all agree upon. But you know, that one's pretty simple, but there's a number of other definitions that may not be so simple. You know, what is a web plastification factor? Now, that might not be here, but it'll definitely be in the notation section later. But yeah, some of these other definitions, you know, what is the engineer of record, things like that. Okay. Now, this section doesn't have a notation component because it's just basic. But if you go to Section 6, actually, you know, for the heck of it, maybe I'll go to Section 6 or Section 3 or something like that, just so that we all understand the organization. Okay, so here's Section 3. Here's the table of contents. There's the scope, all the terms and definitions. Typically, you will also see this, a notation section. So when there is a you know, B prime, what does B prime refer to in all these equations? B prime refers to an equivalent footing width, usually expressed in feet. Where can you find that? In Section 3.11.6.3. So, you know, this is to sort of ensure that you're using the equivalent notation throughout, okay? Some symbols have, you know, multiple terms. I mean, the letter A, there's only so many letters in the alphabet, so maybe it shows up in multiple locations. All right. Make sense? Just so everybody's aware of the organization of the document so that it doesn't scare you too much. Okay. That's Section 2. We'll look at that later. Okay. All right. 1.3, design philosophy. This starts going into the general design philosophy that we use in the spec, which is essentially LRFD. And I mean, you go into limit states, and you know, here's the equation. Equation 1.3.2.1 is the basis of LRFD. Factored resistances must be greater than or equal to factored loads. Okay. Now, just so everybody's clear, so everybody understands what's going on. All right. Zoom in on that real quick. So we've got our nominal resistances adjusted by a resistance factor to achieve or to generate values we can use for design. we also factor our loads. But we don't just take all the loads and add them up and multiply them by 3. You know, we have individual load factors for each, you know, load component. A different load factor for dead loads than we do live loads and what have you. Make sense? Now, what's new and what you might not have seen before are these, okay? Honestly, though, they really don't deserve much time, these ADA factors, okay? Now, let me go into the PowerPoint and show you what's going on. So, I did not hit shift, so start it over. Okay, so going back to this LRFD expression, you can see where I got that, right? Just basic LRFD. These terms are new, these load modifiers, okay? Now, there are 3 load modifiers that go into this. There's one, an N sub D, N sub R, and N sub I. Whatever value that you use for these load modifiers, it's got to be greater than or equal to 9.5. Now, or 0.95, sorry. Now, that's the math. Here's why they don't matter, okay? There are 3 factors that are put in the spec, okay? One is related to ductility, one is related to redundancy, one is related to operational importance. Let's take each of these topics one at a time, because I'm not saying these topics aren't important. They're really important, okay? So let's start off with ductility. Ductility is basically a measure of how much a given element can resist load past its elastic behavior. So you all remember from, I don't know if it was civil engineering materials or construction materials, whatever, you take a piece of steel or a piece of material, what have you, you yank on it, you know, initially it behaves elastically, but there is a point when you yield that material and then you'll get permanent deformations, okay? That range of permanent deformations, how much, you know, permanent deformation it can withstand before it fails, is a simplistic way of expressing its ductility. And usually we would like structures to be very, very ductile, okay? Problem is, we handle ductility in other areas of the spec. We don't need a load factor or some load modifier to account for it. It's the same thing with redundancy and operational importance. Let's take redundancy, okay? Redundancy is another sort of critical term in the world of bridge engineering, and it got a lot of press about 10 years ago when I-35 failed in Minnesota. But basically, redundancy is the idea that if I have a bridge and I have a component of that bridge that fails, can the rest of the system shift around that load and still carry load safely? That's what redundancy is. Does the system have some amount of reserve capacity? Now, number one, redundancy, and I can state this for a fact because I spent a number of years researching this topic. You know, redundancy can be a pretty damn tricky thing to calculate directly. I mean, there's a lot of nonlinear behavior, a lot of 3D, really tough stuff to figure out. But usually, we never really run into it. And I'll give you a really simple example. The bridges that we focus on in here are composite steel girder bridges, you know, slab steel beams, okay? Now, in America, a very common layout would be maybe 4 beams or 5 beams, or if you've got really wide bridges, you use more than that. Very rarely in America would you see a 3 girder bridge currently constructed, and you'd almost never see a 2 girder bridge constructed for a number of reasons. It might be the most economical one, but I can tell you any bridge engineer, any DOH employee will tell you why you'll never see a 2 girder bridge erected here in the United States, and that's because that bridge will be designated as something called fracture critical. And anybody at the DOH knows that term. And when bridge engineers or bridge inspectors hear that term fracture critical, they start to twitch a little bit, and they go, oh, no, let's not do that. The term fracture critical comes from the idea of a bridge that's non-redundant. The idea that if that bridge or that element fails, the bridge is going in the river. Like if I have a bridge that has 2 beams and one of those beams fails, you think that bridge can hold up? Probably not. It's going in the river, okay? So what do? We just erect bridges with 4 beams or 5 beams, and we don't have to worry about it. See what I mean? Pretty simple. So now operational importance, I don't really know if there's much that you can do from a code standpoint, but I do think this is an important quality for bridges to have. I I'm not saying that a bridge that carries traffic in some random county in Nebraska that sees an ADT of about 30, you know, and half of those are children of the corn or something. That's a joke, not a very funny one. But I would argue that a bridge carrying traffic to a trauma surgical wing at a hospital is a little bit more important than some farm road out in Nebraska. Am I okay in saying that? Now, what's more important or less important, or what are those values, you know, those specific lines in the sand that we draw? I don't know that I'm the right guy to answer that. That's why we have a structural engineering community. I would argue that this is an important concept, but this is for the policy folks. This is beyond, I think, the technical design aspects that we're looking at. So I'm not saying that these three qualities are not important. Here's what happened in the spec. You start going into the spec, each of these values are specified to be somewhere in the range of plus or minus 0.5%. So if I was dealing with a value that was 0.95, that would indicate superb performance. 1.05 would be poor performance. Keep in mind, you're modifying the loads, okay? So if you got superb performance, you can cut those loads down a little bit. The reason why it's kind of a bunch of junk is because when they were writing the spec back in '94, they knew they wanted to incorporate this in some fashion, but nobody had done any research, and they didn't have a clue how they were going to do it. So they said, let's just put something in the spec as a placeholder, and we'll get back to it later. Well, nobody really got back to it. Well, they did, but nobody could get back to it in a simple way, you know, come up with a nice little formula or equation that they could use. So anybody tells you that, well, you need to use an N sub D of 1.05 or 0.95, I'd ask them to tell you why, because, yeah. So that's all I got on that. So, all right, moving on. So this was just put in the code as a placeholder. One of the things you'll find in the spec is it's really easy in the engineering community to get something into the spec. It can usually be a little difficult to get something out or get something changed, because once engineers start using something, we get really familiar with it, and we don't like it to change. You know, we have this set of distribution factors that we like. Somebody's going to really have to convince us that we need a new set of distribution factors. Okay, so that's just, you know, the world we live in. All right, so far so good? Okay, now LRFD is all based, and any structural design aspect is typically based around the concept of a limit state, or a condition that we deem to be fairly important during the service life of a bridge. For the world of bridge engineering, we essentially address 4 limit states: service limit states, strength limit states, fatigue and fracture, and extreme event. You could argue that maybe there's a 5th limit state in there that we might call constructability. And constructability is kind of its own thing. That's when you address the bridge's life during construction, and maybe that is the worst scenario. You know, it just depends. I don't know if you'd call it its own limit state, but it's in there. I'm going to take each of these one at a time so we understand what's going on. So, strength limit states. All right. A strength limit state is meant to ensure the bridge can safely withstand the loads it's subjected to, and that's it. So strength limit states are probably the ones that you all are most familiar with in your undergraduate design courses, or if you've taken pre-stress or something like that. You've seen strength limit states before. That's in building design, that's your 1.2 times the dead plus 1.6 times the alive. You factor the loads, you factor the resistances, and you're trying to see whether or not the structure is safe. And it's one of the most fundamental checks that you need to do. That's where the reliability and all that stuff comes into play. There's a famous quote, though, by Hardy Cross, and I don't remember if I have it in the slides or not, but I definitely want to mention it now, and if I do, well, we'll see it later. So does anybody know who Hardy Cross is? All right. So Hardy Cross, first off, if you've ever been to the ASCE Virginia's conference, you probably heard the name. Hardy Cross was a very famous structural engineer who sort of hopped around a little bit. He was originally from Virginia, but he hopped around, was a faculty out in Illinois and whatnot. But he developed a structural analysis method called the moment distribution method. And if you had a structures 2 course or an indeterminate course, you might remember it. It's when you sort of have a highly indeterminate beam and you assume it's all fixed, and you sort of carry your moments over and do this distribution. You can do really complex indeterminate analysis really quickly. There's also a very similar method in hydraulics. If you have a pipe network, you can estimate flow in pipe networks. It's really the same thing. It's the same math principles. In hydraulics, he applied it to pipe systems. In structures, it was to indeterminate beams, but it's all the same thing. And he had a very famous quote about structural engineering, and he said that strength is essential and it's otherwise unimportant. And what I mean by that is that there's so much other crap going on besides the strength limit state that we in here, when we're attacking real life applicable structural engineering problems, we got much more to consider than just this. I mean, there are many structures out there that the strength limit state isn't even the problem. It's fatigue or it's constructability or what have you. So let's take each of these one at a time. So service limit states. Now, a strength limit state is meant to ensure, worst case scenario, can the bridge hold up? A service limit state is trying to ensure that the bridge performs well during day-to-day operation. Typical normal behavior. Trying to limit things like stresses. Trying to limit things like deformations. Trying to limit permanent deformations and yielding. A lot of this really isn't calibrated. There's no statistical calibration or reliability stuff that goes into this. A lot of this is just good old engineering judgment. And now it's engineering judgment based on rigorous assessment of the behavior, but there's not as much calibration that goes into it than there would something like the strength limit state. But they're very critical and very important. One very popular one is live load deflection. We have many bridges out there that are perfectly safe to resist loads, but they're governed by the fact that they couldn't deflect too much. Because if you're driving down the bridge and the bridge is like this, it's not going to be a very comfortable ride for you, is it? Right? You wouldn't like to drive on a bridge like that. I don't know if I'd want to be that person driving since they just got pulled over by the cops. Everybody's looking at the cops and what's going on out there? All right. What's that? Oh, okay. Yeah, I guess, yeah, I see what you mean. All right, so the bridge, so going back to my example, you might have a bridge that's perfectly safe, but it wouldn't be very comfortable to drive if it was like that. We have to limit those deflections just for its usability, so something to be considered. Fatigue and fracture. Now, this one's a really unique one, especially for, I would say especially for steel, but one of the quirky things about material behavior is the concept of fatigue, and it's a really important one in our world, in the world of bridge engineering, because fatigue is a phenomenon that's related to any element that's subjected to cyclic loading, loaded, unloaded, loaded, unloaded, loaded, unloaded, which happens obviously to bridges all the time, right? Now, from a material standpoint, we'll get into this a little later, you might have a steel that has a yield stress of 50 KSI, but you look at a fatigue detail and it can't go above 12 KSI. So you might be limited in some aspects of your design. Your design may be limited solely based on its fatigue performance, okay? And that can't be too surprising if we're talking about bridges. I mean, that's what a bridge is meant for, is for that repetitive loading. All right. Last one is extreme event, and I really don't talk about extreme event very, very much in the course. I just think it's worth mentioning. Extreme event is, it's just what it says it is. It's something that happens that's way beyond day-to-day operation, and it might even be way beyond what we would normally consider to be worst-case scenario. If you've got a bridge with a pier, let's say, in a river, and it's 10 degrees below zero, and you got this big chunk of ice going down the river, and boom, hits the pier. That's an extreme event. You got a car crash into a barrier. That's an extreme event. You've got an earthquake, stuff like that. It's important, yes. I don't spend a lot of time talking about it because we got plenty on our plate with just normal day-to-day bridge operation. So we'll talk about that for the rest of the semester. Maybe if we got some time later on, we'll talk about some extreme event related stuff. All right. Any questions? Okay. Let me see what time it is. Okay, doing this. Yes, sir.
On that extreme event, like you mentioned earthquakes, out here, they're not too common. But out in California, where they're a lot more common, they wouldn't really be extreme. They would be
I get what you're, yeah, I mean, yeah. From a specification development standpoint, we still consider it to be an extreme event because it's not, I mean, in your world, you're saying, oh, well, earthquakes happen every day. And yes, earthquakes are more common out west, but it's not like they're happening every day. You see what I mean? Okay. Yeah, yeah. That's number one. And I'll give you a building design consideration that, that can, I'm going to get off topic a little bit and talk a little bit about building design because I think this is kind of important. Okay, so here's an example. You're in a car with a friend, and if you've had me for class before and heard this example, you don't get the answer. All right, you're in a car with a friend, okay, and your friend is driving, you're in the passenger seat. They don't know what they're doing. They're hitting like 50, 55 miles an hour, and they hit the brake. What's the first thing you slam into? What's the first thing you slam into? You're in the passenger seat. They go 55. They hit the brake. What do you hit? Anybody? I mean. What do they hit? How about the seat belt? Y'all aren't wearing your seat belts? My goodness. Wear your seat belts. Wear your seat belts. No, the point is that would be an extreme event under a passenger state. You know, passengers experience normal behavior, but then you suddenly hit the brakes, something resists you, okay? We do not design the entire car to hold you back in the event of the brakes suddenly being hit. No, we design a select component of that car to hold you back. We call that component a seat belt, okay? Now, here's the thing for buildings, and I use this analogy because I think it's a little easier. For buildings, it's the same. If an earthquake hits a building, it does not, there's no earthquake monster pushing on the building, okay? It does not apply a force to the building. Like what's going on in the car, though, it doesn't apply a force. It accelerates the building. I mean, why do you fling forward when somebody hits the brake? It's because the acceleration suddenly changed. You move. The force comes from the fact that you're accelerating. You have a mass. Force equals mass times acceleration. That mass is that force is transferred to the seat belt. And that's the force that the seat belt. A building to resist that earthquake force. Where the extreme event comes into play is this. The way we handle earthquake engineering and earthquake design is so fundamentally different to the way that we handle day-to-day operation design. You know, this building is subjected to another very significant lateral load, okay? In the world of structural engineering, we have two very, very main lateral loads that go like this. One of them is earthquakes. What's the other? Wind, okay? Now, wind wouldn't be an extreme event, would it? No, wind happens all the time, right? I'm sure there's some breeze right now, okay? This building gets hit with wind, okay? After that wind goes away, we don't want to have to rebuild the structure from scratch, do we? We would like the structure to be able to resist that wind in some fashion. Seismic design, earthquake engineering is different, okay? Our goal in seismic design is one thing. We want the people in the building to not die, and that's it. If we have to completely rebuild the building from scratch, that's fine, okay? That's totally fine, as long as everybody can get out safe, okay? Now, one of the ways we get around that is through fuses, okay? Now, what do I mean by fuse? Why do we have fuse panels in houses? Why do you have a fuse box in a house? What is its purpose? What does that do? Why would you want to prevent a circuit overload? Exactly. Okay, now, makes sense, right? Now I'm going to say what he said again, but from a structural engineering standpoint. What he said is that we are placing an element in the system that's purpose is to fail. Now, that's a weird concept for a structural engineer to hear the first time they heard it. You placed an element in that system. In this case, it's an electrical system, and we call that element a fuse. But you placed an element inside that system, its purpose is to fail before the whole thing does. Okay? Make sense? In buildings, we do the same thing. We place structural fuses inside buildings that their purpose is to fail and absorb that energy so that, the building doesn't fall down. Or and going back to my car crash example, okay? You go, let's say we're designing vehicles. If you wanted to design a vehicle that remained elastic after a car crash, that sort of acted like a bouncy ball. You took that car, slammed it into the wall, and it didn't have any deformation. It responded, and it went back to the same as it was after the car crash. If you designed a car like that, I guarantee you one of two things would happen. Number one, you would never find an engine powerful enough to transport that massive car from one point or another, because you would have this massive structure, wouldn't be able to power it unless we had some nuclear engine or something. And two, that car crash would be transferred to the person in the car. All that energy would be transferred to the driver, kill him like that. Okay? Instead, we design cars to fail in a similar fashion. I mean, if you've seen a car in a car wreck, it's a mess. After a car wreck, it's a mess, right? It's deformed, it's crinkled up and what have you. We design that car so that the car absorbs that energy. It's the part that deforms. It's the part that absorbs that energy, but hopefully so that you don't, so that you're not the one that dies. It's the same philosophy. Car might be totaled to hell, but you're not dead, or, as best we can, or designed as best we can. Make sense? Okay, so to go back to your question, I know I went a long way around answering your question, but your question was, can't earthquakes, they're not really an extreme event in the area of California. I get what you're saying, but it's still not really the case, because our entire design philosophy and our motivation is completely different. And that's a really good question, okay? Did that clear that? I think I know I took a little bit of time on that, but I thought that was valid. That was a good point to bring up. Everybody good? All right. Okay. So now what I want to do is I want to look at Section 3. So maybe what you all ought to do is you all have a Section 3 packet with you, right? You might want to do your best to follow along with me. Now, a lot of this stuff I'm going through really quickly. Like, I'm not going to go through the table of contents or the terminology or the notation or any of that crap. I want to get into really what it is Section 3.4. 3.4 is where we're going to start to get into the loads and the actual limit states that we use. Now, like I said, there are strength limit states. The bridge spec lists 5 of them. And we're going to take them one at a time so that you understand what they are and why they're there. In building design, I don't know that it's as specifically laid out like this, like it is in the world of bridges. You've probably seen 1.4 times the dead, 1.2 times the dead, plus 1.6 times the alive, and you see all these load combos. And up until now, you probably thought, let's just put the loads in there, and the biggest number that we use, or the biggest number that we get, that's the one that we use for design. And yeah, there's some truth to that, but usually each of those load combos has a specific purpose, okay? Same thing here. These load combinations that we're going to see, they each have a specific purpose, and I want to lay that out. So first one's strength 1. Strength 1 limit state, every structure has to meet strength 1. That's just basic use of the structure. Dead loads, live loads, is it safe? Basic. Okay. Now, strength 2 is one that you probably won't hear many people talking to. Strength 2 is basically the specifications device to be able to handle the way different states do things. In other words, take Kentucky. We're going to talk about the live loads that we use in bridges later, and Kentucky says, that's great. We're going to take those live loads and bump them up 25%. Why? Because that's Kentucky and that's what we do. Okay? Now, that's an oversimplification. Kentucky sees, heavier truck traffic, and if that's what they need to do, that's what they need to do. What does Strength 2 say? Strength 2, load combination relating to the use of the bridge by owner-specified special design vehicles, evaluation permit vehicles, or both without wind. The idea is this is the code's way of saying if you're, Kentucky, or if you're Nebraska, or if you're wherever, and you've got to use a heavier vehicle, use Strength 2, and that's basically what it's saying. And usually state specifications who use heavier vehicles, they're writing around this is essentially what they're doing. Sound good? All right. Now, the other three combos are related to either construction or wind, okay? I might show you a video next time of what can happen during construction when you've got heavy winds and you don't brace effectively. But strength 3 is saying, okay, we've got normal use of the bridge, but it's being exposed to large winds. Now, that can be a big consideration. Usually in its finished state, we like to assume that all that wind gets transferred into the deck, into that diaphragm action in the deck, and that deck is so stiff, nothing's going to happen. But during construction, if you're dealing with a bridge that's got 12-foot deep plate girders, which happens if you've got these really long spans, and wind hits it, that's a significant pressure acting over a really big area. You can get some really big wind effects on I-beams. And I-beams are really weak in the weak axis, so they can deform pretty quickly. You can get some crazy stresses going on. So that's where, you know, strength 3 and what have you. Strength 4, this is a really big one during construction. Very high dead to live load force effects. You know, during construction, there's no trucks on the bridge, but there's a lot of dead load, okay? So that's where that's coming from. All right? Sound good? All right. So, difference between strength 3 and strength 4. Strength 3 is if you've got a really, really heavy wind on it. Strength 4 or strength 5 is if you've got a wind and vehicles on it at the same time. That's where the difference comes in. All right. Service limit states. Okay. Service 1 and service 2. Service 1 is the one that sort of is applied to all bridges. Service 2 is specifically a steel bridge limit state, and it's trying to limit the permanent deformations in some of your flanges and trying to, in other words, trying to control yielding. Now, service 3 and 4, you can read those over, and if you've had pre-stressed, you know exactly what that stuff is. It's all talking about the limits of crack control and things like that in pre-stress. Now, you know, service 4 is pre-stressed concrete columns, so if you had a pier or something that was pre-stressed, you'd apply that. All right. Sound good? Okay. Fatigue. Okay, now this isn't going to make a lot of sense right now, but this will make sense later when we start digging into fatigue. But fatigue is a phenomenon that's obviously a function of the number of cycles. You know, more cycles, you can get different capacities. There is a point, however, and this is, you know, we can start getting into the literature and into the data. There is a point when, I don't care how many cycles of load you put on it, there's a certain threshold stress that we say you can put 2 million cycles or 200 million cycles. It's still not going to be any more than 12 KSI. Okay? And that's the difference between what we call infinite life and finite life. So infinite life is we use a constant threshold stress and we say, all right, that's the maximum stress that section can see regardless of how many cycles of load there is. Finite life is if you've got a bridge with low traffic, you might have it might be advantageous in your design to take into account the fact that you don't have much traffic and you can get increased capacity due to fatigue. Now, if it was me and you're in doubt, I would just go with infinite life because then you don't have to worry 10, 20 years down the road when the traffic increases and now your bridge doesn't work. So that's just me. So when in doubt, I would go with infinite life. That's just me. All right. Extreme movement 1 and 2. 1 is your earthquake load and 2 is basically everything else. All right. Now, what you all are used to, 1.4 dead, 1.2 dead plus 1.6 live, what have you. All these load combos in the spec, instead of laying them out in equations, they're laid out in this table. So you all should see a table in the spec that looks something about like this. Okay? So strength 1, strength 2, strength 3, da, 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 da. All right. Now, so each of those are these load combos. Now, what these letters up here are basically the individual load components that we need to factor. Now, you're probably used to D standing for dead load, and L standing for live load, and S standing for snow load. Well, there's a lot more stuff in the bridge spec. There's a lot more different components. For instance, DC is the dead load of the components of the structure, the actual physical structure. DW is the self or the weight of the future wearing surface. Like if they go and they put asphalt over it, and you go, well, why do they need to split those up? It's because there's a whole lot more variability with how much asphalt they put on the structure versus how thick the concrete deck is. LL is the vehicular live load. IM is the dynamic impact factor and what have you. EQ, that's your earthquake load and what have you. All right. Now most of these are numbers. Like the live load factor is 1.75, so they're a little bit larger. Okay. I'll talk about why here in a second. But you notice some of them have these gamma P's. We'll try and simplify that here in a second. Now, first thing that we can do is, let's see if we can simplify this a little bit. Number one, for the purposes of what we're talking about right now, we're only talking about composite steel girder bridges. So we don't need to deal with things like that service 3 and service 4 or any of that. Second, we don't need to deal with any of these load components up here that have anything to do with pre-stressing. We don't need to deal with creep or shrinkage or relaxation. It's steel. We don't have to worry about it. So I can take this and I can simplify it quite a bit. Okay? Also, there's a lot of stuff up here related to curved forces, you know, things like that, braking forces and whatnot. For now, I'm going to eliminate anything related to curvature. We can talk about curve bridges maybe a little later. So we really only need to worry about 3 main force effects right now: dead load, live load, and wind loads. And some of you could go, wait a minute, it's West Virginia. What's going on with that snow? True, yeah, bridges see snow. But in our load model, we incorporate a 64 pound per square foot load anyways for vehicular traffic. That 64 pounds per square foot is way larger than any snow load we'd see around here with a ground snow load of 20 PSF. That's number one. Number two, typically we don't like our bridges to be, yay deep in snow. We'd like to see them used. That's why you have trucks going on all over the place, plowing them out and whatnot. All right, so what I've done here with this table is I way simplified it. I knocked out anything that had to do with curvature, with pre-stressed, any limit states we didn't need to consider. Breaks up pretty easily, right? The blue stuff, the shaded stuff, that's the only stuff we really need to consider, okay? The only thing we haven't really explained are these gamma sub P's, okay? These gamma sub P's are the load factors for the permanent loads, the ones that don't sit there, or the ones that always sit there. In the spec deals with maximums and minimums for the permanent loads. The reason why it specifies maximum or minimums is because if you've got a structure that's got a really odd geometry, there's a possibility that you might have a lot of load over here on this span, and this one span over here might want to uplift. So in order to account for worst case scenarios, there's maximums and minimums. But for most regular structures, we shouldn't have to worry about that. So for instance, if I look at the dead load, the dead load of the components and attachments, I have a maximum and minimum load factor. In most cases, you're just going to go with the maximum. That make sense? Excuse me. All right, sound good? All right, so there are, let's see, what do I have here? There are some additional notes that I'm going to make in regards to construction loads. These are just food for, points for food for thought later. We're going to spend a fair amount of time talking about constructability. It is a topic that needs to be addressed with care. You need to make sure that you're doing your analysis and getting your forces and moments correctly, because if not, you can really screw up a construction project. So we'll talk about that later. So if I go through that table, I knock out all the stuff that doesn't matter to me assessing a composite steel girder bridge and start breaking it up. These are my load combinations that I really need to assess. Now, if you notice, these load factors are a little different. Like you're probably used to 1.2 dead and 1.6 live. This is 1.25 times the dead and 1.75 times the live. The reason why, I guess 6 to 1, half a dozen to the other, if you look at your phi values, phi is 1. They bumped up the load factors, I guess, so that the resistance factors, they didn't have to incorporate them. I don't know, I guess that took the stink off of folks doing design that didn't like LRFD very much. I don't know. There's, like I said, going back to a point I made earlier, once you get something in the spec, it's really hard to take it out. And there's a lot of engineers that they really didn't like LRFD when it first came into the limelight, because LRFD is more complicated than allowable stress. Take a capacity, divide it by 2, and there you go. It seems simple. It's also not as economical, so that's sort of what sold it. All right, so here's our load combos for strength, service 2, and fatigue. And again, there's other stuff going on with construction. It's not as simple to just talk about right now. We got to talk about that later. So we'll hit that up later. Anybody have any questions? Okay. We're making pretty good time, so this is what I'm going to do. All right. You all have a homework assignment that I think you all are fairly well situated on, so we're going to leave that one at that. That one's due next week. What we're going to do next week, probably the week after, it might even bleed a little bit in the week after that, is we're going to handle side 1 of the equation, the loads. Okay, so we're going to talk about what is DC, what is the live load, what is a dynamic impact factor. Define all that. Take that bridge that we looked at earlier, and I mean go through and fully calculate. Start to finish. Okay? It is not something that's done quickly. It takes time. Okay? One of the nice things about it, though, is it's loads are loads. It doesn't matter if it's a steel bridge, bridge made out of popsicle sticks, it doesn't matter. Okay? So it's pretty generic. Then we'll take the other side of the equation and handle the resistance. Any questions? Then that's all I have for you all tonight. You all, again, remember, don't forget your homework assignments. Submit it on MU Online. I'll see you all next week.